One of the biggest challenges for modern astrophysics is to describe how the universe went from a uniform place without planets, stars, or galaxies to the rich, structured, diverse cosmos we see today. Not just with a general story, mind you, but in gory detail, going not only as far back as we can see, but even farther, to what must have existed at an epoch where even our most distant observations are insufficient to take us there. Going back to the limits of what's observable, to when the universe was just a few 100 million years old, we find a slew of fascinating objects under James Webb's views. Stars and star clusters exist in abundance. Galaxies with perhaps up to 1 billion stars light up the universe. Even quasars with very large black holes formed early on, well before the universe was even 1 billion years old. It's the old chicken and egg problem made new. If there's a maximum rate at which black holes can grow, and the universe wasn't born with them, how did we make the ones that we see? In other words, how did the universe make such ultra-massive black holes in such short periods of time? And now, after decades of conflicting stories, scientists finally think they know what happened. But I warn you, that will blow your mind.
It is a crazy idea, and I admit it's a crazy idea. The trouble is, it seems it's quite likely it's true.
Join us as we dig deep into how James Webb's supermassive black holes actually arose. Just 50 to 100 million years after the Big Bang, the very first stars of all began to form. Massive gas clouds started to collapse, but because they were made up of hydrogen and helium alone, they struggled to radiate heat away and dissipate their energy. As a result, these clumps that gravitationally form and grow need to get much more massive than clumps that form stars today, and that has repercussions for what kinds of stars form, as well as what kinds of astrophysical processes occur alongside their formation. While today, typically, we form stars that are about 40% the mass of the Sun, the very first stars were about 25 times more massive, on average. Because the matter that leads to these stars, streams of gas, need to cool in order to collapse. It's only the largest, most massive clumps that form early on that will lead to stars. The average first star might be 10 times as massive as our Sun, with many individual stars reaching hundreds or even thousands of solar masses. In addition to these effects, there are cold, flowing streams of gas that collide and intersect, creating regions of dense, cold, neutral matter that rise up to tens of thousands, or perhaps even hundreds of thousands, of solar masses. There's long been a tension in cosmology between what's expected and what's observed. Are the black holes that form at the centers of galaxies made from the mergers and growth of stellar remnants alone, or was there a different mechanism at play, such as either the formation of primordial black holes that the universe was born with, or from the formation of large seed black holes that arise independently of stars and stellar cataclysms? Let's first consider the from stars and stellar remnants alone route. Most of the first-generation stars that form will end their life in a supernova, leading to either a neutron star or a small, low-mass black hole. But without any heavy elements at all, the most massive stars will reach such high temperatures in their cores that photons, the individual particles of light, can become so energetic that they will spontaneously begin to produce matter and antimatter pairs from pure energy alone. You may have heard of Einstein's E equals mc squared, and this is perhaps its most powerful application. A pure form of energy, like photons, can create massive particles so long as the fundamental quantum rules governing nature are obeyed. The easiest way to make matter and antimatter is to have photons produce an electron-positron pair, which will happen all on its own if temperatures are high enough, and happens in some of the most massive stars, even today. In these ultramassive stars, as in all stars, gravitation is attempting to pull all of that matter in towards the center. But photons and all of the radiation produced in the cores of these stars pushes back and holds the star up, preventing its collapse. This happens independent of the star's mass, as that balance point must be achieved inside any object that isn't going to vary, oscillate, collapse, or explode. However, in these most massive stars, the radiation pressure is higher, the temperatures are higher, and the high-energy processes that occur are more numerous, including this phenomenon known as pair production. When you start producing electron-positron pairs from these photons, however, some of that radiation pressure drops as photons, which move at the speed of light, exert a greater amount of outward pressure than massive particles that move at speeds slower than light. Rising up to a temperature great enough to produce these electron-positrons pairs also depletes your star's ability to hold itself up against gravitational collapse. And while it's true that there are a few narrow mass ranges that lead to the star destroying itself entirely, a large fraction of cases will result in the entire star directly collapsing to form a black hole. The direct collapse scenario that has been observed in a few incidents even in the late-time universe. This is a remarkable step. It means that the most massive stars of all, with many hundreds or even thousands of solar masses, can form when the universe is just 100 million years old or so, less than 1% of its current age. These stars will burn through their nuclear fuel the fastest in 1 or 2 million years, tops. And then, their cores will get so hot they'll start turning photons into particles and antiparticles, which causes the star to collapse and heat up even faster. Once you cross a certain threshold, all you can do is collapse. And this isn't just theory either. We've actually seen stars directly collapse without a supernova, leading directly to what could only be a black hole. But that's only the beginning. Whenever you have a large cluster of massive objects acting primarily under the force of gravity, different objects get kicked around from these interactions. The least massive objects are the ones that are the easiest to eject, while the most massive objects are the toughest to eject. As these stars, gas clouds, clumps, and black holes dance around, they undergo what's known as mass segregation. The heaviest objects fall to the gravitational center, where they interact and can even merge. All of a sudden, instead of a few hundred black holes of a few hundred or a few thousand solar masses, you can wind up with one single black hole of approximately 100,000 solar masses or even more. Remarkably, that might not even be the fastest way to grow a massive seed for a supermassive black hole to form out of in our cosmic history. Just as massive enough stars can directly collapse to a black hole without a stellar cataclysm, it's thought that a dense, massive, and cold enough population of gas can directly collapse to a black hole, perhaps even without a single star at all as an intermediary. This scenario recently got bolstered by an unexpected observation, made by combining both NASA Chandra X-ray data and James Webb Space Telescope data of galaxies from the ultra-distant universe. In Webb's data, a distant, faint, low-surface brightness galaxy was found from around 500 million years after the Big Bang, a galaxy that contains only around 10 million, maybe up to 100 million, but not more than that, solar masses worth of stars within it. However, in this galaxy, an active, feeding, X-ray emitting black hole of around 9 million solar masses exists, which raises new questions about where black holes came from. The big issue is that we've already seen large, relatively grown-up black holes, even in the early universe, of hundreds of millions or even over 1 billion solar masses after just several 100 million years of cosmic evolution. These black holes can grow in bursts that typically exceed the maximum rate of growth or the Eddington rate that's sustainably allowed over long time periods. But if we trace that growth back to when we need a seed to grow from, those seeds must have been tens of thousands or even hundreds of thousands of solar masses to begin from. Starting from a stellar mass seed won't work. You might think to take the black holes from a single star cluster, merge them together, bring other star clusters with their own black holes in, and have them merge as well. But even that can't grow what we call an overmassive black hole, or a black hole whose mass is comparable to the mass of all stars within a galaxy combined. The fact that such a galaxy exists tells us that no, merging stellar mass black holes together, even en masse, can't be the sole way that we made supermassive black holes in the universe. Some sort of massive seed, more massive than standard star formation allows for, is required. One theory is that these black holes got a head start in their mass accretion processes by growing from smaller black hole seed. And early supermassive black holes could have grown from heavy seed black holes with huge masses around 100,000 times the mass of the Sun. These would have formed directly from the collapse of massive clouds of matter, thus skipping the star stage of other black holes entirely. Astronomers refer to such black holes as direct collapse black holes. These direct collapse black holes could then grow alongside galactic mergers, which were commonplace in the early universe, that would also bring supplies of gas and dust for these voids feast upon. Then eventually, other black holes might have collided and merged with those. John Reagan, a research fellow at Maynooth University, compares this to the 6-foot-tall toddler being born with a length of 3 feet. It is still a bit confusing and perhaps a tad disturbing, but it better explains how the toddler reached the size of an adult so rapidly, at least more easily, than if the toddler started off with the length of an average infant. Regardless, the authors themselves point out the limitations of their research and urge caution with extrapolating that the growth of the black hole captured by James Webb reached supermassive status. A very interesting idea came from Nobel Laureate Roger Penrose. The impossible supermassive black holes could be the black hole of previous universe created our universe. In the simplest possible terms, Sir Roger Penrose believes that our universe is not the first, nor will it be the last, to spawn from a dense mass of highly ordered everything into the complex universe we see around us. The current Big Bang model, which is partially grounded in inflation, doesn't supply a reason as to why a low-entropy, highly ordered state existed at the birth of our universe. That is, unless things were set in motion long before the Big Bang actually occurred. In Penrose's theory, our universe has and will again return to a state of low entropy as it approaches its final days of expanding into eventual nothingness, leaving behind a cold, dark, featureless abyss. By virtue, black holes, the vacuum cleaners of our universe, which leak radiation and destroy everything they touch, spend their cosmic lifetimes working to scrub entropy from the universe. As the universe nears the end of its expansion, the remainder of its black holes will evaporate or gobble one another up, thus setting things back into a state of order. During this period, the universe would begin to revert back into a similar state it was in at the Big Bang, when the geometry of space-time will become smooth again, which is in stark contrast to its current jagged form. According to Penrose's model, this will usher in the new aeon, after the universe is no longer able to expand any further. So it collapses back in on itself as a highly ordered system, one that is ready to trigger the next Big Bang. The current model of the universe says that any temperature variations in the cosmic microwave background should be random or Gaussian, but Penrose claims that he and his partner Vahe Gurzadian, who hails from the Yerevan Physics Institute in Armenia, have found more than 12 very clear concentric circles within the data, which was collected by NASA's WOMAP satellite over the course of a 7-year period, where there are regions where the radiation have a much smaller temperature range. To him, these posits are spherical evidence of the gravitational waves, massive ripples in spacetime that are created through the collision of massive black holes, which took place during the previous aeon. Of course, if his hypothesis, which has been dubbed conformal cyclic cosmology, were validated, it would suggest that the current state of our universe is merely one of perhaps an infinite number of aeons, which also mean there is no need for a precursor for the Big Bang. I claim that this aeon is one of a succession of such things, where the remote future of the previous aeons somehow becomes the Big Bang of our aeon, Penrose said. Of course, his conclusion has been criticized amongst other physicists, but it's still an interesting hypothesis with vast implications. After all, one thing can't be denied. Black holes are one of the most mysterious and interesting marvels in the macrocosm that always fascinate our minds. So let's close out today's video with the most impressive, extraordinary, and shocking black hole stories of 2023. 1. One of the biggest supermassive black holes. In March, researchers revealed that they had found what may be one of the most massive black holes ever discovered. The cosmic titan sits at the heart of the elliptical galaxy Abell 1201 BCG, located 2.73 billion light-years from Earth, and the galaxy itself is in a massive cluster of galaxies called Abell 1201. The Abell 1201 BCG black hole is believed to have a mass equivalent to 32.7 billion suns and was discovered through the effect of its gravitational influence on space. This is one of the biggest ever detected, and on the upper limit of how large we believe black holes can theoretically become. So it is an extremely exciting discovery. 2. Supermassive black hole seeds in the early universe. For many years, scientists have pondered how supermassive black holes reach such tremendous sizes. This is particularly challenging when supermassive black holes with millions or billions of times the mass of the Sun are discovered in the early epoch of the universe, when they would not have had time to feed on matter or even merge with other black holes enough to reach such titanic masses. In August, astronomers discovered evidence of how this process may get a head start, finding heavy seeds of black holes with masses around 40 million times that of the Sun in the universe just 400 million years after it began. These so-called outsized black hole galaxies are believed to form directly from massive clouds of gas and dust, rather than from dying stars, saving billions of years on the path to supermassive status. 3. Supermassive black hole. Merger close to Earth. In October, astronomers discovered a supermassive black hole binary system in the aftermath of two merging galaxies. At just 90 million light-years away, it's the closest pair of supermassive black holes to Earth yet discovered. The black holes have masses 54 million times that of the Sun and 6.3 million times that of the Sun, respectively. Currently, they orbit each other at a respectable distance of 1,600 light-years. But in around 250 million years, they will spiral together and merge, just as their parent galaxies did 1 billion years ago, creating a daughter supermassive black hole with a combined mass of around 60 million solar masses. 4. Echo of supermassive black hole's monstrous burp. In June, NASA's imaging X-ray polarimetry explorer caught the echoes of an outburst from our galaxy's supermassive black hole, Sagittarius A star. Sagittarius A star is believed to have belched this high-energy light around the turn of the 19th century, and scientists caught its echo in the form of X-rays shining from dense molecular clouds of gas surrounding the center of the Milky Way and birthing new stars. The 200-year-old burst of radiation is believed to be the result of a chunk of an asteroid, a gas cloud, or a star venturing too close to Sagittarius A star, and being shredded by the immense tidal forces generated by the supermassive black hole's intense gravity. 5. Black hole's AI makeover. In April, the first ever image of a black hole, dubbed the fuzzy orange donut because it is notoriously blurry, got a major makeover thanks to AI. To improve the sharpness of the image, researchers used a supercomputer running a machine learning technique called Principal Component Interferometric Modeling, or PRIMO for short. This allowed them to fill in the gaps missed by the Event Horizon Telescope, or EHT, when it captured the first image of the black hole in 2019, and to slim down the glowing ring of the supermassive black hole to learn more about it. As Todd Lauer, an EHT member and NOIR lab researcher, said in a statement, "Primo is a new approach to the difficult task of constructing images from EHT observations. It provides a way to compensate for the missing information about the object being observed, which is required to generate the image that would have been seen using a single gigantic radio telescope the size of the Earth." 6 million light-year-long Jedi lightsaber from a black hole. In November, researchers studied the black hole Messier 87 and its jets to see how they release energy. This energy isn't coming from within the black hole. The boundaries of black holes, called event horizons, prevent anything from escaping. Instead, the spinning of the black hole twists up magnetic fields, which slow its rotational speed and then launches highly collimated jets of material that the team described as million light-year-long Jedi lightsabers. If you took the Earth, turned it all into TNT, and blew it up 1,000 times a second for millions and millions of years, that's the amount of energy that we're getting out of M87, said team member George Wong, a researcher at Princeton University. 7. The first ever direct image of a black hole jet, and yes, M87 again. In April, a collimated blast of energy emerging from M87's supermassive black hole became the first black hole jet to be directly imaged. The image shows, for the first time, how the base of the jet connects to matter, swirling around the supermassive black hole and gradually being fed to it. As team member Eduardo Ros, a scientist at the Max Planck Institute for Radio Astronomy, we plan to observe the region around the black hole at the center of M87 at different radio wavelengths to further study the emission of the jet. The coming years will be exciting, as we will be able to learn more about what happens near one of the most mysterious regions in the universe. 8. Black hole pointed right at Earth. In March, astronomers watched for the first time as the jets launched from the active heart of a galaxy powered by a feeding supermassive black hole switched direction and pointed straight at Earth. The galaxy PBCJ 2333.9-2343, located around 656 million light-years from Earth, had been seen emitting jets but had appeared to fall quiet until firing up again and realigning its jet by 90 degrees to point at Earth. The team behind the observation described this as a very exceptional case of jet reorientation. 9. Supermassive black holes that recycle. Scientists knew that supermassive black holes are messy eaters, but they didn't realize that black holes may have light diets because they recycle a lot of the material they fail to consume. In November, astronomers discovered material engaged in an intricate dance around the supermassive black hole at the heart of the Circinus galaxy, located around 13 million light-years away. They found that the central black hole feeds on only around 3% of the material that falls toward it, and the energy it generates pushes the rest away, meaning it is a much lighter eater than previously thought. That doesn't mean this matter keeps its distance, however. Much of it falls back to the central supermassive black hole in an arrangement almost akin to a water fountain. 10. Back-to-back black hole records. In April, astronomers used the Gaia spacecraft to discover what seemed to be the closest black holes to Earth. Designated Gaia BH1 and Gaia BH2, the black holes are located 1,560 and 3,800 light-years away, respectively. But just a few months later, scientists discovered that there may be several black holes in the High 80s cluster, which, at just 150 light-years away, would make them 10 times closer than Gaia BH1. These 2, or possibly 3, black holes could be even more remarkable because they might not be in the dense star cluster at all, but were ejected from the Hyades 150 million years ago to wander the Milky Way alone. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.